The red bars are not increasing over time, whereas the weather-related ones are. And so we're seeing this increasing trend in the number of natural catastrophes due to weather events. Now, those examples that I showed you in the beginning there all have something in common, and that is that they're all related to weather patterns that are very, very persistent, or you might think of them as getting stuck. So, you know, if it's dry for a couple weeks, that's not a big deal, but if it goes on for months or even years, then we're talking about drought. Same for that stormy winter in Boston, for example, where it wasn't just a couple of snowstorms. We were in a pattern where we were getting snowstorm after snowstorm after snowstorm. So this is the kind of extreme events that I'm talking about when we're looking at how the Arctic might be playing a role. So let's just set the stage a little bit here. And what we're looking at is on the bottom are the months of the year, and we're looking at global average temperatures on the vertical axis. And so in the warmest years on record in the human experience are shown on this graph. We have 2010, 2014, and 2015. So those are all the warmest years except for 2016. And when we put this on the graph, we see that we are in a very disturbing situation here where we're getting warmer and warmer, and already we're bumping up against that 1.5 degrees centigrade increase that the Paris Agreement has set as a limit. So you see we're already uncomfortably close to that 1.5 degree limit, and this is for global temperatures above normal. And one of the manifestations of the globe warming so fast is that the Arctic sea ice, and this is the ice that's floating on the Arctic Ocean, is disappearing, and undoubtedly you've heard about this. But we can actually think about how what we're seeing in the recent period relates to the behavior of the ice going back about 1,500 years. So this is some work that has looked at how the ice in the summertime has changed based on sediments in the bottom of the Arctic Ocean. And this chart shows you, going back that far, how the sea ice extends. So this is the area or the real estate covered by sea ice on the Arctic Ocean. And you can see there's a lot of ups and downs and wiggles and things, but it's pretty steady over this period until you get up to modern times. And that blue dotted curve on the right there shows you how things have been changing lately, although it only goes up to the early 2000s. So if we look at what happened in 2012, which was the all-time record low amount of sea ice during the summer, what we find is that the number doesn't even fit on this graph. We are clearly in uncharted territory. And if we put the last several years on this chart, we see that we're hovering around that record territory ever since. So this is a very different situation that we're in. And in fact, if you calculate just the change that we're looking at in 2012 relative to the past, we've lost literally half of the ice covering the Arctic Ocean in the summertime. And then if you take into account the thickness and calculate the volume, we've lost almost 3/4 of the sea ice floating in the Arctic Ocean, and that's occurred only in the last 30 years. So, you know, our lifetime. Not only has the ice disappeared in terms of extent, and I mentioned the volume already, but this animation is showing us how the thickness of the ice has changed as well. So going back to the early 1980s and going forward up to present, up till 2016, those colors, you can see the chart, the color scale on the bottom shows you how over this very short time period, the thickness of that ice has really disappeared. It's really gotten thin. And this is a concern because that thin ice is much more vulnerable to any shifts in winds or shifts in ocean currents. And so if we get an anomalous or an unusual weather pattern up in the Arctic, it can blow a lot more of that ice right out of the Arctic into the North Atlantic. So it's a much more vulnerable ice cover now than it used to be. And why do we care about this ice disappearing so much? Well, one of the reasons is that, as we know, ice is very white. It reflects most of the sun's energy when it hits it. And on this graph here, the white area, we're looking down on the North Pole here, is showing what the ice cover looked like in 2012, that record year, compared to what it should be, which is that pink line that encircles it. So because we're losing so much ice, instead of that sunshine being reflected back to outer space, it's now going right into the ocean. It's heating up the ocean. It's melting even more ice and setting up what we call is a positive feedback. So we melt ice, we absorb more energy from the sun, warms the water, melts more ice. So this is one of the reasons why the Arctic is warming 2 to 3 times faster than it is on the globe as a whole. Now we can look at that warming in another way. This is looking down on the Arctic again. The North Pole is right in the middle. This is the difference from normal of the temperatures during the wintertime over the last 25 years. So during that period where the ice has really been disappearing. And what this is showing is that it's much, much warmer over the North Pole and surrounding the North Pole over most of the Arctic Ocean. And actually what we see, which is very interesting, is cooling happening over the continent. So on the right there is Asia. You see that those colors, those blue colors are telling us that it's colder than normal. And in the eastern part of North America, over on the left side, is also an area of colder than normal temperatures. What is going on with that? Well, we'll talk about that a little bit later. So we can look at that another way, too, and see how over time, starting in the late 1940s, how the temperatures in the Arctic, which are in blue, have been changing compared to the temperatures in what we call the mid-latitude. So that's between 30 north and 60 north, which is where we all live for the most part. And what you notice right away is that the mid-latitudes have been warming very slowly relative to the Arctic again. And this is something that we call Arctic amplification, this extra fast warming that's happening in the Arctic compared to everywhere else. And what you'll see here is that in 2016, this metric we call Arctic amplification was the largest we've ever seen. So this is another very disturbing piece of information. I also just want you to notice that this signal of Arctic amplification really started to ramp up in around 1990 or the mid-1990s. So again, this is a very recent phenomenon, and one of the issues related to this is that because it's so recent, there are not very many years where we have this strong signal in the Arctic, and so that makes it somewhat difficult to be able to measure how the atmosphere is responding to that. When we have a short number of years, it makes the statistics more complicated, and so this is something I want you to keep in mind. So why do we care about the Arctic warming faster than everywhere else? Well, I'll try to explain that very simply. If we think about a layer of air that's extending from, say, North America up to the Arctic, and we know that when the air is warmer, which it is in North America compared to up in the Arctic, warm air expands, and so that layer is actually thicker here compared to the way it is up in the Arctic. And this forms a hill in the atmosphere. If you were sitting on top of that layer, it would look like it was sloping downhill as you look towards the north. So air sitting on top of that layer wants to flow down that hill, just like water wants to flow down the side of a mountain. And what does that do? It creates a wind. So that wind, though, because the Earth is spinning, gets turned to the right in the northern hemisphere. And this becomes what we call the jet stream. All right, so think back now to what I said about Arctic amplification. We know that the air is warming much faster in the Arctic than it is here, and so the effect is that that layer of air is getting thicker in the Arctic than it is here, and so it's making that hill less steep. So there's less force driving that wind, and we see that, in fact, the jet stream then becomes weaker because of this more rapid warming in the Arctic. And it turns out that when the jet stream has weaker west to east winds in it, it tends to meander north and south more. It has these bigger waves, and we're going to talk more about that coming up here. So here's this idea that we've been working on for a long time. We see that the Arctic is warming really fast. We see that extreme weather events are increasing, and we're wondering, are they connected? Well, here's some more evidence. This is just for 2016 now. This is the 12 months of 2016 on the horizontal axis. And the vertical axis is going up into the atmosphere. So from the surface up into what we call the stratosphere, way up there. And these pink and blue blobs are showing us how that layer of the atmosphere I was just showing you has been either higher than normal, which is when they're red, so it means that the Arctic air is warm and it's bumping those layers up, or the blue colors are the opposite. So what you see is that there are these episodic events in the Arctic, and this is just for north of 70 degrees north, so looking at the Arctic cap. And those red blobs there are very episodic. We see these periods where the Arctic is extremely warm, and then it might cool off a little bit. Well, these very warm periods, it turns out, are associated with a whole variety of extreme weather events. So in the winter months, say anything from snowstorms and stormy periods to flooding to severe cold events. And then you look at the summer months in the middle there, you see flooding, you see anomalous melting on Greenland surface, heat waves, and so forth. So we're not saying that every single extreme event is associated with one of these warm episodes in the Arctic, but certainly when we get these warm episodes, we tend to see a lot of extreme events happening around the Northern Hemisphere. But of course, the question is, how is this happening? What are the mechanisms that we think are connecting the warming in the Arctic to these wavy atmospheric patterns, these wavy jet stream patterns, and these extreme weather events? Well, that's what I want to tell you about today. There's been a lot of research going on, and I think we're getting a better handle on how this works. So, a couple of effects of Arctic amplification that are standing out. This one I've already mentioned. We know that when the Arctic warms faster than mid-latitudes, we tend to get weaker west-to-east winds in the jet stream, and we also are tending to see what we call intensified ridges, or these northward bulges in the jet stream are getting bigger and stronger. Now, in both cases, the result is this. The left figure there down at the bottom where it says strong is a case in November when we had a lot of cold air parked over the middle of the Arctic, and the red arrows encircling it there are a kind of a schematic showing that when we have a very, very cold Arctic, we tend to get a relatively straight flowing jet stream around that cold air in the Arctic. But on the right there, you can see that the blue blobs there are not centered over the Arctic anymore. They've migrated southward down over North America and down over Asia. We see that those red arrows are now much squigglier, taking bigger swings northward and southward. And this is what we see happening when we get these strong bouts of Arctic amplification. So why do we care about these wiggly waves in the jet stream? Well, it turns out that those waves in the jet stream are really what control our weather. Now, here's a schematic of a typical jet stream over North America. First, you notice that purple arrow there is signifying this river of fast-moving wind that we call the jet stream. It separates the cold air to the north from the warm air to the south. But in addition to that, the different parts of the wave, this part, for example, that's over the western part of North America, is where we find the dry and settled weather conditions, the beautiful clear blue skies that you picture on a cold winter day or on a hot summer day for that matter. So that part of the jet stream wave where the winds are out of the northwest tend to be dry and settled weather, whereas where the winds are coming from the southwest is where we tend to get the storms forming. So this is a common pattern that we see in the winter where we tend to get these storms forming along the east coast of the U.S. We get this part of the jet stream over our heads. So the question then is, how do we measure what's going on with these waves in the jet stream? One of the ways we're doing this is to think of that layer of air that I was talking about in terms of a topographic map that you might use for hiking. So here we're looking down on the North Pole again, and we're looking at these red colors here that indicate where the thickness of that layer is high, so that that layer is very high up in the atmosphere, and then the blue colors are where the layer is very thin. That means that the air is cold. And then where we find these lines are very close together, these lines of constant thickness, you know that if you're a hiker, when those lines are very close together, it means that hillside is very, very steep. Well, the same happens in the atmosphere. When those lines are close together, it means that hill is really steep, and that's where we find the strongest winds. And then we can, where those lines are very close together. So what we do then is we pick one of those lines that is in that very tightly packed region, and we can track what those lines are doing over time. We can track the shape of the waves and how they move in space and change in time. One of the metrics that we're using now, and this is a very new research that's just been published last month, as a matter of fact, is a metric we call sinuosity. And it's a very simple concept. And basically, the blue line that we're showing here is one of those lines from that previous graph. That's a line of constant thickness of the atmosphere. The red line is a latitude circle. So what we do is we take one of these lines from that topographic map, we calculate how much area it encompasses, and then we find the latitude circle that has the same area. And if we take the ratio of the length of the blue line to the red line, we get a measure of wiggliness, if you will. So the wigglier that blue line is, the bigger the sinuosity is. So here are two examples. Here's a case when those lines are very straight going across North America, and we find that the value of this sinuosity is very low. But when we see those lines taking a lot of big swings northward and southward, we get a much larger value of the sinuosity. So this is giving us an indication of basically how wavy the jet stream is. So let's look at what's been happening with sinuosity over the last couple of decades. So these plots now are showing you the trends, so the changes in time of the speed of the west to east winds in the jet stream. Time is along the bottom axis, and latitude is on the vertical axis, so going from 30 up to about 80 degrees north. So where you see blue colors there, the way you read this is you start at a particular time, and the trend is from that time to present. So let's start at 1980, for example, and you see there are blue colors there. That means that the speed of those west to east winds in the jet stream in that latitude range have been decreasing over that time period. Now let's compare that to what's been going on with the sinuosity. What we see is that in the same areas where the winds have been weakening, we see an increase in the value of the sinuosity. So this is giving us some confidence that when we see weaker winds in the jet stream, we indeed see the jet stream getting wavier. So this is for the past. Now let's look at the future. And the nice thing about sinuosity is we can do it for any data set. We can use it for the actual atmosphere of the past, or we can look at climate model projections for the future. So what I'm going to show you now is how the winds and the sinuosity in the future, which is the end of this century, compared to the past over North America, are changing in the model. So here we're first looking at January, and along the bottom are the values of sinuosity, and along the top are the changes in the west to east winds of the jet stream with latitude on the vertical axis. So this is for the winter time. So when we see the winds, when the wind values are strong or positive, that means that they're stronger in the future relative to the past. And when they're negative, it means they're weakening in the future. So what we see is that in the subtropics, the winds are projected to increase, but in mid-latitudes, they're projected to decrease. That's the blue curve. And you can see that together with that is the red curve, showing that as the winds weaken in those mid-latitudes, we're seeing an increase in that sinuosity, which means it's wavier when the winds are weaker. Similarly, for the summertime, this is for the month of August. This is interesting because we see this really strong peak in the sinuosity right about at 40 degrees north, right over the United States, combined with, again, that weakening of the zonal winds. So this is an indication that the loss of snow cover during the summertime in the spring, which is a very strong signal of climate change, is leading to this pattern in the atmosphere, this Arctic amplification over the continents that is weakening the winds and driving this big increase in the sinuosity, making those waves in the jet stream even bigger. And we know that when those waves get bigger in the jet stream, they tend to move much more slowly, and it leads to very slow changes in our weather patterns, leading to those persistent weather patterns that I talked about in the very beginning. Okay, I see that I'm running out of time here, so we'll go quickly through this next concept. And this is a new hypothesis that we've just published, actually, called It Takes Two to Tango. And this is the explanation, perhaps, for those intensifying ridges that I mentioned. So if we look at the Pacific Ocean here in North America, this is a schematic. You see all the ice in the Arctic Ocean to the north there. This is back in the good old days when we had lots of ice up there. And if we had one of these big waves in the jet stream come along, there really wasn't much influence of the ice on that wave because it really didn't change much from year to year. But if we fast forward now to what's happening today, we see that this ice is being lost. In particular, here's an area north of Alaska. I told you that when we lose that ice, we gain a lot more heat in the ocean. And so when a wave in the jet stream comes along, it depends very much on where that wave is located as to whether that heat has any influence or not. If the ridge in the wave is not located near that heat source, it's going to have no effect. But if it happens to be located near that heat source, then we see a building of that ridge. It makes the ridge stronger, the wave bigger, and the progression of that wave more slow. So again, that leads to a more persistent weather pattern. And we can see this happening in many studies that have come out over the last really just 5 years or so. You can see them listed here. And what we're noticing here, we're looking at Asia, and you remember I talked about how Asia is actually getting colder with time as the Arctic gets warmer. Well, if we see that there's this natural ridge that happens right over Western Asia, it's also a location where we see a lot of sea ice being lost. And so that sea ice loss and that heat that's gained in the ocean there is intensifying that ridge and making the whole jet stream wavier, which is that blue curve that's encircling the North America there, or Northern Hemisphere. And when that jet stream gets wavier, that wave energy gets transferred up to the stratosphere, which also disrupts the polar vortex, which is actually up in the stratosphere, and that makes this effect of that ice loss and warming persist through the winter and lead to these bigger waves that persist and cause that cold temperatures over Asia. So really quickly, just want to tell you about one more really interesting thing that seems to be emerging, and this is more in the summertime. We know that in the summer, again, these big waves tend to cause the heat waves and flooding events that we observe in the summer. But in particular, we're noticing that when the jet stream splits into two parts, and here's an example looking at Europe, where those bright colors are showing where the strongest winds are both to the north and to the south of Europe. When these split jets happen, it tends to trap the waves of the jet stream and holds them in place. We call it a waveguide. And this tends to happen more often when the jet is weak. So again, a weakening jet stream because of Arctic amplification is favoring these split jet conditions, which tends to make the waves in the jet stream basically get stuck. And this new work by Michael Mann and his group are showing that the split jet over time, going back to the 1800s, which is the black curve, has been increasing, especially recently, and that corresponds very well with the overall warming of the northern hemisphere and especially Arctic amplification. So there seems to be a link between Arctic amplification and these conditions of split jets. And why is this whole story so controversial? Well, it's really because the atmosphere is so darn complicated. So here's just to kind of give you an idea of all the things that we're dealing with. We're trying to figure out whether the mid-latitude weather patterns really are changing, but they're affected by so many things, changes in storm tracks, jet streams, these big waves, and those in turn are affected by many things as well. Some of them are natural, as you can see on the right there, and some of them on the left are related to human activity and global climate change, global warming, and Arctic amplification. So it's really a very complicated story, but we really are starting to get a handle on some of these mechanisms. And this is just to drive home the point. We're looking at real winds of the jet stream here. Those bright yellow and red colors are the real winds of the jet stream, just to show you how very complicated the circulation of the atmosphere is. Sometimes those waves are small, and when they are, you can see they move quickly, but when they grow large, they tend to stay in one place much longer. But all these other swirls and features in the atmosphere are they put a lot of noise in the system and make it very difficult to tease out changes over time. So with that, I'll say thank you very much.